Welcome to Maths with EJD. We're still talking about real analysis, and we're considering some special kind of project under real analysis as we've been done with the key aspects some few videos back. So here we're looking at some pathological functions. Of course, the idea of pathology in this case would tell you about some functions that have some behavior that are unexpected or some unprecedented behavior, right? Some strange behavior. Okay. So the kind of pathological function we're looking at in this place is the continuous but nowhere differentiable functions, right? Continuous but nowhere differentiable. Now, it's established that differentiability is only possible, differentiability of a function is only possible if the function is continuous, right? So, but it's possible to have some continuous functions which are not differentiable. Okay, so we go on to look at the objective of this video. So first of all, we define the Weierstrass function W, and then we sketch why W, the Weierstrass function, is continuous everywhere but nowhere differentiable. And we visualize roughness via multi-scale zooms and difference quotient experiments. Then we'll compare with the Takagi Blancmange function. So straight to the point, we have definition and basic properties. Definition and basic properties. Okay, so here we define the Weierstrass function, 1872. So let 0 be less than A be less than 1. That means A lies between 0 and 1, and B is greater than or equal to 3, an odd integer, and AB is greater than 1. So look at all the conditions now. So A lies between 0 and 1, while B is greater than or equal to 3. And then A multiplied by B is greater than 1. So it means that, so for instance, A can be something like, say, 0 point, okay, maybe not 0 point now. A can be 1 over 3. Okay, A can be 1 over 3, right? Maybe A can be, say, 2 over 3. Yeah, A can be 2 over 3. So that by the time you multiply that, you have 2. So in that case, AB is greater than 1. So they can define the, I think this one should actually stand out. Okay, it should really stand out like that. So we double that. Yeah, good. So then you can define the Weierstrass function W of x to be summation from n equals 0 to infinity of a raised power n cos b raised power n pi x for x belonging to the real number system. So we have some basic facts. Each term is continuous. So you see that the absolute value of a n cos b raised power n pi x is less than or equal to a raised power n itself. And since the summation of an converges by the Weierstrass M test, of course, it makes sense that it converges because it's between 0 and 1. A is between 0 and 1. So A is a fraction. As the value of n increases, that will definitely converge to 0. So by the Weierstrass M test, the series converges uniformly on the real number system. Hence, the Weierstrass function is continuous everywhere, a uniform limit of continuous function. So continuity is established. However, let's go. W is one periodic and even. So we have W of x plus 1 is the same thing as W of x. And then W of minus x is equal to W of x. So one periodic means that, so after every one period, it comes back to the original point. That's why W of x plus 1 is W of x. And it is even because W of minus x is equal to x. So something like, okay, well, that may not be a perfect example there, but let me just leave that. Then we have the heuristic roughness. So at scale b raised power minus m, the n equals m term oscillates with frequency b raised power m and amplitude a raised power m. So if AB is greater than 1, its slope contribution behaves like AB raised power m, which explodes as m approaches infinity. Okay, so let's look at nowhere differentiability and with a proof sketch. Nowhere differentiability with a proof sketch now. So fix x to be a number on the real number line and consider HM to be B raised per minus n, then we have the Weierstrass, we have some relationship of Weierstrass functions like W of x plus HM minus W of x all over HM is equal to summation from n equals 0 to infinity of A raised per n cos B raised per n pi into x plus HM minus cos B raised per n pi x all over HM now. So the dominant layer NM, so using cos theta plus pi minus cos theta, which is equal to minus 2 cos theta, we have this expression now, cos b raised per n pi into x plus hm minus cos b raised per n pi x over hm is close to 2 over hm, and that is equal to 2b raised to the power m, because of course, h over m is b raised per minus m, so the b raised per m just comes up like that. So the n equals m term has size approximately a raised per m, b raised per m, which is equal to ab raised to power m, right? So for other layers, now apart from the dominant layer, for n not equal to m here, the contributions can be bounded uniformly by a geometric series. They cannot cancel the growth of the dominant layer. Then in conclusion, if AB is greater than 1, then AB raised power m approaches infinity. So along the sequence HM, the difference quotients are unbounded. Hence, W prime of x cannot exist at any x. Then we have a regularity note. The Weierstrass function is holder continuous of any other alpha which is less than minus log A over log B, right? Talking about the interval now, AB, and of no larger order. So this exponent will appear in the empirical modulus of continuity experiment below. So we have the Takagi Blankmange function for comparison. So define phi of x to be this x comma z, that's the distance to the nearest integer. Then we see that t of x is equal to summation from n equals 0 to infinity of 1 over 2 raised to power n, phi of 2 raised to power nx, where x belongs to the closed interval 0, comma 1. So like w omega t is continuous everywhere and nowhere differentiable. So at finite stages, it is polygonal and corners proliferate at dyadic rationals like that. Okay, so let's look at a Python implementation of all these things we've been talking about. So imagine let's talk about some parameters and core helpers. So here we import the necessary libraries, which are basically NumPy and Matplotlib, NumPy for numerical computations, Matplotlib for visualization. So we define all these parameters now. A is 0.5, B is 7, N is 30, minimum is 0, max is 1, number is 8001, X naught is 0.313. That is point to zoom around and probe derivatives, right? Zoom windows, you have different windows like that. 1 times 10 raised to minus 1, 5 times 10 raised to minus 2, 2 times 10 raised to minus 2, 1 times 10 raised to minus 2, and 5 times 10 raised to minus 3, as you can see here. So we have A, comma, B, comma, N, params A, params B, param N now is equal to all this, right? So we now have Weierstrass function truncated for numerics. So we define a function, okay? This is all the things I've been talking about so far. Then we can then define a function called Weierstrass. X is that takes S, then A is 0.5, B is 7, N is 30, and we have X is NP dot as array X, NP dot a range N, like that. Now it returns A raised power N cos B raised power N pi X, and the axis is 0. So therefore, the Takagi Blankmange helpers, we define phi of X, which is distance to nearest integer. So we have absolute value X minus round X. Then we define Takagi that X m equals 20. Then you have, and what that returns is phi of 2 raised power nx all over 2 raised power n, like that. And then the utility, you have uniform tail bound for convergence check. So you also define another function, Weierstrass tail bound, A start index, so geometric tail. You have some end start and so on and so forth. So with that in place now, we just have, so we can run this. So that sets the stage for the other things you're going to be seeing. So we have just defined all the things we need for subsequent ones. So if we talk about the global plots and multi-scale zooms for Weierstrass now. So for the global domain, we have X, which is NP length space params, minimum, maximum, and number of X. Then we have the W, which is the Weierstrass, which takes X, A equals A, B equals B, N equals N, all the values we've declared before. And then you have this figure which plots Weierstrass function against X with line width 1. The plot title is Weierstrass function, with all this A, B, and N that we are going to see as we run it. Then we have zoom near X naught. You have all the zoom near X naught also. So we run that. So we have all these plots. So you have Weierstrass function W of X, A is 0.5, B is 7, N is 30, like that. So this is W of X against X, like that, from 0 to 1 on the X-axis, and then you have all this. Then taking X naught to be 0.313, and we take window plus or minus 0.1. So this one that we have X ranging from maybe somewhere close to 0.225 to 0.4, and we have W of X on the Y-axis. Then we have this for the win. So the first window is plus or minus 0.19. It's plus or minus 0.05. We have this, okay, like that. And then we have window plus or minus 0.2. We have this. Then plus or minus 0.1, we have this. And then plus or minus 0.005. We also have this. Now, because X naught there is 0.313. Let me see if I can do if I can do some latex stuff. Okay, yeah, that works. X naught. Okay, so beyond that, we also have the convergence sanity checks. You have uniform bound plus partial sums. So here, everything is still dependent on the first set of parameters we defined. So here now we have the tail bound, we have sup of X sum over for n equals n greater than or equal to n for an cos, all those values. And that is less than or equal to a raised by n over 1 minus a. So for k in 10, 15, 20, 25, 30, and we print n, two decimal places, I think, where you have unit form tail bound less than or equal to the Weierstrass tail bound, a comma k, 3e. Then we compare partial sums in sup num over the grid. So you define the Weierstrass partial, and you have this, and you have k as 5, 10, 15, 20, like that. So if you run this, you get the convergence sanity check. So here now you have different values. So n equals 10, uniform tail bound is less than or equal to this value, 1.953 times 10 raised to the power minus 3, all the way to n30, n equals 30. So it keeps, is it reducing? It actually keeps, it's reducing, yes, it's reducing, because this is 10 raised to the power minus 3, this is 10 raised to the power minus 5. So it keeps reducing all the way down to 1.863 times 10 raised to the power minus 9. So the bigger the n, the smaller the uniform tail bound. Okay, then you have S10 minus S5 over grid like that. So you take that's the norm to infinity over the grid. So all those also keep decreasing like that. So as we compare 5, 10, 15, 10, 20, 15, 20, 25, 20, and 30, 25. Okay, then we can define quotient experiment. So which blow up along HM equals B minus M. So here we have differential coefficient at this. So we define HS empty, D is empty. Of course, differential quotient at is take X naught, A, B, N, and then max is 12. So you have HS is D that. Then for M in range, you have all these expressions. And then you can run this and you get the difference coefficient experiment, which blow up at HM equals that. So you have all these values now. You have all these results. So you have the H values, first of all, then you have the absolute value of difference quotient, all those that way now. So these are the results we get right there. So the interpretation of this is that if the absolute value of W of X naught plus H minus W of X naught all over H grows without bound as H approaches zero, along H equals B raised to minus M, that is consistent with nowhere differentiability. So that gives us nowhere differentiability. Then we have empirical Holder exponent via modulus of continuity. So again, this is still based on what we did before. So this one is going to estimate alpha from W of H, which is approximately C H alpha, where W of H is the supremum of the absolute value of 2 minus S less than or equal to H. Then absolute value of, supremum sub this, right, of absolute value of W of 2 minus W of S, which is estimated on a grid. So we have this whole code thing going, and then we run this and we get some results here. You get this kind of thing. So we have the theoretical Holder exponent alpha star to be minus log A over log B, which is approximately 0.356. Empirical slope, which is approximately Holder exponent, gives alpha equals 0.357. So we have the empirical modulus continuity like this. So we have H log on the x-axis and W of H on the y-axis. Then talking about the Takagi function, then we have plot plus quick difference quotient proof. So here, you plot Takagi Blancmange function. So T is Takagi taking X, M equals 20. So you plot the figure. So difference quotients are dyadic sequence. H equals 2 raised power minus M. So you have this as to supply H is 2 raised power minus M, X1 is X0 plus H, and all these other things. And then we try to visualize the Takagi function, right? So see what we get. It's this thing that looks like a cloud. So you have the Takagi Blancmange function on 0, 1 like that. Then you also have the difference quotient for Takagi. That's what we get here. And then we get the Takagi difference coefficient 0.48, 0, 0.920, 0.6, 0.7, 0.84, 3.44, 3.00, 3.76, 3.00, and 2.96. So those are the Takagi difference coefficients in that case, you know. So this is the Takagi function right here. Okay, so we have T of X on the y-axis and then X on the x-axis. So now what to look for in the outputs, right? Normally when you deal with this, what do you look for in the outputs? So you look for continuity. So smooth convergence of partial sums and stable curves. That talks about continuity. All right. Then we have roughness at every scale. Zooms show persistent jaggedness. So you can see the jaggedness. So you have this, nothing is smooth. It just keeps going like that, you know. So then nowhere differentiability for numerical heuristic. Difference quotient grow as H approaches 0. So you can see the difference quotient we got here. So it keeps difference quotient grow as H approaches 0 along H equals B raised to minus M like that. Okay. So you can see all that. Then we have the Holder behavior slope alpha in cell 5 should be close to minus log A over log B, right? Okay, I think there's no cell 5, there's no any cell 5 here. So in short, slope alpha, like we saw, okay, slope alpha should be close to minus log A over log B. So I think we saw minus log A over log B somewhere. Is it here? Yeah, we saw it previously, I think. With that, my approximate 0.376. I think it should be here. Yeah. So that's minus log A over log B like this. So it should be close to, it is expected to be close to minus log A over log B. So you can see the slope 0.357. It is close to minus log A over log B as expected. Okay, then we have the Takagi comparison. Polygonal look, but still nowhere differentiable. So it looks like a polygon, right? It's Takagi comparison. So you have this looking like a polygon, but it's not differentiable anywhere. Okay, so It's continuous everywhere but not differentiable. So suggested exercises, you can do some parameter sweep. You can try A is 0.6, B is 5, and A is 0.4, B is 11. Compare empirical Holder exponent. And other phases, replace cos by cos plus dot plus theta. Nothing essential changes. Alternative step sequences. Test random H approaching 0. Note volatility versus tuned H equals B raised for minus M. And we have modulus of continuity fit. Make the grid denser and confirm the slope stability. So with this, we'll come to the end of this video about pathological functions, talking about everywhere continuous but nowhere differentiable functions like that. So that's the kind of pathology that you have a function that is continuous but it's not differentiable. All right. So that brings us to the end of this interesting video. In the next video, we'll be talking about another kind of pathological function. Right. Let me know how helpful this video is for you. And if there's something like a trial, feel very free to let me know. If you have subscribed already, thank you so much. If you haven't subscribed, of course, you don't want to keep missing out on this channel. So feel free to hit the subscription button. And having done that, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can take it a step further. You can become a member of this channel by clicking on the uh, join button, and that gives you grants you access to 3 levels of membership. At the highest level of membership, we can get to hang out one-on-one on any of the things I discuss on my channel, be it on mathematics or scholarships or data, anything related to data like that, right? And of course, ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. So, like, come your way again. Keep doing maths right. Bye.